Welcome you all to the week 1 problem solving session of Advanced Calculus for Engineers. Myself Guru Bachan from Department of Mathematics, IIT Jodhpur. I am working in the broad area of fractal geometry and dynamical systems. In today's session, we cover the topics Rolle's theorem, mean values theorem, and Taylor's theorem, and at last indeterminate forms. So we first recall the conceptual criteria or conceptual statement of the theorems and with their geometrical interpretation. Then we will discuss some examples related to them. So let me start with recalling Rolle's theorem. So I hope screen is visible to you. So
Yes.
thank you. So let me start with Rolle's theorem. So what Rolle's theorem says, let f be any function from a closed interval ab to r, and if f is, first one is continuous on whole interval ab, second one is differentiable on open interval ab, third one is fa is equal to fb. So here I am using some abbreviation, so let me write it here first. From next now onwards I will write continuous as this abbreviation. So f of a equal to f of b. If these three conditions f satisfy, then our statement, our Rolle's theorem says that guarantees the existence of there exists a c in open interval ab such that this derivative of f at c is 0. So can anybody tell me why here we are taking open interval in case of differentiability? Any guesses? Here we are taking it as closed interval, but here we are considering as open interval. Any idea?
Don't get the question.
I'm asking why we are considering here, why we are talking about here open interval rather than talking about the closed interval. See, while we are talking, yes, please, someone's trying to say something.
Left hand limit differentiation not exist at the left side
Okay,
for one type. For one more side, right hand side differentiation won't be exist.
okay. So let me explain it. So first of all, what is the geometrical interpretation of this particular theorem? Suppose this is our function f, and this is your point B, this is your point A. So clearly f is continuous because there is no break in the graph. Next is differentiability. So the clear or the direct way to see the differentiability, you can see that whether our graph contains some peaks or not. So here you can see that there is no peak. So we can say that in between this interval AB, open interval I am talking about, we can say that our function is differentiable. Next, f of a is equal to f of b. It is visible here. So there must exist a C by the Rolle's theorem such that f dash of C is 0. Now what is the meaning of this f dash C is 0? Let me tell you that first. F dash x means slope of tangent line to f at x naught comma f of x naught. And since this f dash C is 0, that means, and one more thing is that it is also called as angle from x-axis. So since f dash C is 0, and usually we wrote slope as tan theta f dash of x naught. So f dash C 0, that means theta must be 0, or you can say theta must be making an angle with x-axis at parallel. So here you can clearly see that there are 3 points that can behave as C. That's what we have told here. There exists at least a number, at least a, or you may write precisely at least a C in AB such that f dash of C is 0. But here we got 3C, 3 values of C, you can say that. So that means the Rolle's theorem's interpretation is like this. We can have more than one C also. Next is, my question was why we are talking about only the open interval. The answer to that question is that, as I'm telling you, that there must be a possibility that before this a, our function may not be differentiable, or it may have some different tangent. So for differentiability, suppose this is a function mod x. So if you will observe that this function is not differentiable at x equal to 0. Why? Because while you trying to draw the tangents, suppose this is the tangent and this is the different tangent. So while we are talking about the differentiability, there must be a unique tangent at that particular point. For example, if you will see at this point, there is only tangent that is parallel to this. But here in this scenario, there are two tangents. So that is why we say directly that our function mod x is not differentiable at x equal to 0. That is why in the starting I was saying, to see the differentiability in the graph, you just need to see specifically where are the peaks. Wherever there is a peak, you can say that directly that function is not differentiable, or you can even roughly assume what are the tangents. If there are two tangents, then you can say that that function is not differentiable at that point. That is why we are talking about only the open interval, because we cannot guarantee what is going to be happen before a or after b. Okay, so this is the Rolle's theorem statement and its geometrical interpretation. Let us apply to this some question. So let f be a function from 0 5 to r, be the function defined by fx is equal to 2x square and 5 minus x by 2. So in the first case, our interval is 0 1. In the second case, our interval is open 1 to 5. So then we need to tell for which values, or you can say for you can say, then tell the interval where C lies such that for that C our f dash is 0. So ultimately we need to check whether this function is satisfying Rolle's statement of hypothesis of Rolle's theorem, and if it is satisfying, then we need to tell, or we need to guarantee that in which interval this C exists such that this f dash C is 0. So since we are aware about this statement, the first one is we need to check continuity on whole interval, differentiability, and our f of a must be f of b. So here if you will see, a is 0 and b is 5. In this case, a is 0, b is 5. I am taking the case where our function is defined from 0 to 5 to r. I am taking the whole domain. You can also apply the Rolle's theorem in the partition like 0, 1 to r. I am firstly considering the whole case. So if I am taking the whole scenario, now we need to first of all check whether this function f is continuous on whole interval or not. Now if you will observe that in the interval 0, 1, this function is 2x square. It's a polynomial. So we can say that f is continuous on closed interval 0, 1 as 2x square is a polynomial. Now f is also continuous on open interval 1 to 5, and clearly this is also a polynomial with, or you can say, as 5 minus x by 2 is a polynomial. Now what is our criteria just to check at 1 what is happening? So to check continuity, because the function is breaking at 1, so we cannot guarantee directly that a function is continuous at 1 or not. So what we do, we calculate left hand limit and we calculate right hand limit and the functional value. If these both limits are existing and they are equal with the functional value, then we can say our function is continuous at 1. So what is left hand limit? 1 minus f of x. We know that whenever we see x any value less than 1, our function will be 2x square. So this will be nothing but limit x tending to 1 minus 2x square. So this can be written as limit h tends to 0, 2 into 1 minus h whole square. Because it is 1 minus, so I am putting as 1 minus h where h tends to 0. So this will be limit h tends to 0, 1 plus h square minus 2h. So this will be 2. Now what will be f of 1? Clearly 1 contained in this interval, so f of 1 will be 2. Next is limit x tending to 1 plus f of x. So in case of we are coming from the positive side of 1 or right hand side of 1, you can say that the function is 5 minus x by 2. So this is 5 minus x by 2. So if you will substitute x as 1 plus h, so this will be 1 plus h divided by 2. So this will give us limit h tends to 0, 4 minus h divided by 2. So when you substitute h as 0, so it will give you value 2. So you can see that limit x tends to 1 minus f of x is same as limit x tends to 1 plus f of x is same as f of 1. Therefore, f is continuous on whole interval 1 to 5. Is it clear to everybody? Can we talk about the differentiability here? Can we talk about the differentiability here? Anyone?
It is not differentiable at x is equal to 1.
Yes, exactly. So this is not differentiable. So let me tell the reason why it is not differentiable. Clearly, it's a polynomial between 0 to 1 and even after 1 to 5. So we can guarantee the existence of differentiability between 0 and 1, between the interval 0, 1 and also in the interval 1 to 5. But we cannot guarantee about 1. So let me mention it. So this was the first hypothesis. The second one is f is differentiable on the interval 0, 1 and the interval 1, 5 as it is a polynomial. But since we are talking about the whole interval 1 to 5, sorry, is there some error? So here it
0
will
to
be,
5.
yeah, here it will be 0 to 5. Yes, you're right. So we are talking about the whole interval 0 to 5. So we want to make sure our function should be differentiable in the whole interval 0 to 5. So to do that, we need to check the differentiability at x equal to 1. So similar to the above one, how we can check the differentiability for this case? So it is like that. So we check limit h tends to 0 minus, you can say left hand derivative and right hand derivative that we need to check. So it can be written as h tends to 0 minus f of 1 minus h minus f of 1 divided by minus h. Tell me if I am writing anything wrong. Next is for the right hand derivative, we need to check h tends to 0 f of 1 plus h minus f of 1 divided by h. So these two quantity we need to calculate. If they are coming out to be equal, then we can say that our function is differentiable. So for the first one, you can say left hand derivative. So this will be f of 1 minus h minus f of 1 divided by minus h. So in the interval before the value 1, our function is nothing but 2x square. So this will be 2 into 1 minus h square. Here it is 2. H tends to 0 divided by h. In fact minus h. So this will give us h tends to 0, the value 2 plus 2h square minus 4h minus 2 divided by minus h. So clearly 2 and 2 will cancel out and we will left with only h tends to 0, 4 minus 2 of h. When you substitute h equal to 0, you will get the value 4. So the left hand derivative of our function f is 4, while the right hand derivative will be 1 plus h minus f of 1 divided by h, which will be equal to limit h tends to 0. So when we are talking about after 1, our function is 5 minus x. So here it will be 5 minus 1 plus h divided by 2 minus 2 divided by h. So this will be limit h tends to 0. This will be, you can say, 4 minus h minus 4 divided by 2h. So this will come out to be limit h tends to 0 minus h divided by 2h, that is nothing but minus half. So clearly the left hand derivative is not equal to the right hand derivative. So limit h tends to 0, f 1 minus h minus f of 1 divided by minus h is not equal to limit h tends to 0, f of 1 plus h minus f of 1 divided by h. Therefore, f is not differentiable on, or we can say at x equal to 1. And the third one condition was, just we were checking it, f of 0 is 2 into 0 square 0, f of 5 is 5 minus 5 divided by 2 0. So from here we can say that f of 0 is equal to f of 5. So you can say that two conditions of the Rolle's theorem are being satisfied, but differentiability is not being satisfied. So we can say that therefore f does not satisfy all the conditions of the Rolle's theorem. On which interval? Since we have taken the whole interval 0 to 5. So we can say on the whole interval 0 to 5, our function does not satisfy the Rolle's theorem's conditions. So we cannot guarantee the existence of such c such that f dash c is 0. Can you comment over the interval 0 to 1, or you can say 1 to 5? First of all, can we talk about applying Rolle's theorem over these intervals? Can we talk about applying Rolle's theorem over these intervals? Yeah, in these two cases, can we talk about?
f of a not equal to f of b. F of 0 not equal to f of 1.
Yes. First of all, for this case is correct. F of 0 is not equal to f of 1. So obviously condition of Rolle's theorem will not going to be satisfied. Okay. What about in this case?
Same thing.
But one is not in the case. One is not in the domain.
One is not in the domain. Yes. We have to check for 1 plus h.
No. See, let us be clear with some basics that this theorem is applicable only on the closed interval. That is why I asked that can we apply or can we discuss Rolle's theorem? We can discuss only in the case of closed interval. Okay. Since here it is a semi-closed interval, so obviously it is not even a good candidate to discuss its applicability of the Rolle's theorem. Okay.
It is essential part for Rolle's theorem.
Yes, it is essential part of the Rolle's theorem. You can say that.
Sir, can you please remind me about open interval of differentiability just to confirm RHD and LHD, na? To come overcome with the issue of RHD and LHD.
Could you repeat, please, your question?
Why was we taken open interval A to B for differentiability? Just to deal with RHD and LHD, na, for on that point.
Yeah, just to make just to avoid these kind of cases. See, if you will not, suppose I am taking about this mod x, okay, on this interval 0 to 1, suppose, okay. If you will say that your function is differentiable on 0 1, what if it will like this and there will be some more tangent? So you cannot say that what will going to be happen left hand side of the 0. So to be precise, or to be make it a good candidate of Rolle's theorem, we can only guarantee the differentiability inside the interval. At the corner points we cannot say anything specifically for differentiability because of the tangent scenario, as I told you. Okay, I hope that is what you were asking.
Yes, sir.
Okay, so let us move to one more problem regarding this Rolle's theorem. This time you will try it first.
Sir, what is the conclusion of the problem 1? So you wanted to ask till the interval where C lies such that
Here,
f dash
here,
C is equal to 0.
here. I have written does not satisfy the Rolle's theorem, so obviously there will not be an interval. Or you can
So
say
we do not have any interval such that f dash C is equal to 0
yes, exactly. So let me
in the
write
interval, in the entire interval 0 to 5.
yes. Hence, there does not exist any C in 0 to 5 such that f dash C is 0. Clear? Thank you for mentioning.
Yes,
So
sir.
let me
Sir,
yes.
talk about left hand limit, right hand limit, and with respect to tangents, left hand limit, right hand limit. How can we, separate it in not differentiability condition?
In this
S-
scenario you are asking about?
yes, sir. Yes, sir. In this.
Okay. So for that we need to first draw its graph. So let us see that how it will look like. So we will write the second question after it. So let us draw this graph. See, what it was our interval? Our interval was starting from 0, okay, and it's going till 5, and at 1 it's breaking. So in this 0 to 1 our function is 2x square. So how it will start? It will start from 0 and at 1 it will go to some value 2. Okay, and what will happen in case of 5 minus x by 2? So y equal to 5 minus x by 2. So how this line will look like? So it will start from 2 and at 5 it is going to 0, so it will be like this. So I hope you are considering it as a straight line. Okay, now let us discuss the differentiability as we have talked about. See, here our graph is going to like this in this scenario. So let me draw it more curvy so that we can see its tangent, how its tangent will move. So its tangent will go like this. It will start from 0. It's like a parabola. Okay, so its corresponding tangent here at 1 will be like this, while over the straight line what will be the tangent? It is like this. At point 1 there are two tangents, and to guarantee the you can say differentiability at any point, we must have a unique tangent, or you can say unique direction of tangent. Is it clear now?
Yes, sir. Yes, sir. Usually we are talking about the differentiability, right hand limit,
Yes,
left
yes.
hand,
I understood.
like
This is
that.
also
That
good.
one.
This is also good point to discuss so that
Yes, yes,
we
yes, sir.
can get
We are.
that pictorial image. How we can talk about the differentiability as one asked about.
Yes, sir. Yes, sir.
So,
Thank you, sir.
please. So let me write one more question. Suppose the function f is given by f of x is 1 plus 2x, while in the another part it is 1 minus 2x 2bx plus 1. Here if x is less than 0, and here if x is greater than equal to 0. And we are saying that this function satisfies the assumptions of the Rolle's theorem. Over which interval? Over, or you can say on, the interval minus half to half. See, obviously you cannot talk about the whole domain because it is minus infinity to infinity. As I told you, we need a compact interval or a closed interval. In simplicity I say. So I am saying that this is your closed interval. Now find the value of p so that this condition f satisfy. That means f is following the Rolle's theorem. So following that hypothesis or conditions or assumptions, we need to tell the appropriate value of p. So we know that our function must be continuous in this whole interval. Our function must be differentiable in the inside this interval, and f of minus half must be equal to f of half. So try this one, then I'll let you know whether answer is correct and we will discuss it. First of all, try it at your own and tell me the value of p.
2.
Correct? Absolutely correct. Let us give some time to others also. So someone told the answer 2, p equal to 2. So how did you get to know about it, that it will be 2?
Sir, by testing the differentiability at x is equal to 0.
Correct, correct. So let me mention it here.
Yes, sir, by doing the same.
Okay. So
And it's a linear function, so we can easily differentiate it directly
okay.
rather than RHD, LHD. Basic linear function, so we can do it.
See,
Direct differentiation is possible.
yes, possible, but let me say one thing here. We can do the derivative only in the case then when we know that our function is differentiable. Okay, with the precise definition of the differentiability I'm telling you. If the function is not differentiable at some point, then obviously there is no point of doing differentiability, or you can say derivative. So I go with the basic approach with left hand and right hand derivative, although before 0 and after 0 clearly it is a polynomial, and we can say that it is continuous and it is differentiable for other points rather than 0. So the point is we need to only discuss what is going to be happen at 0. So the first one is f is continuous on the whole interval minus half to half. Second one is f is differentiable on minus half to 0 and 0 to half. See, now what is happening at 0? So limit h tends to 0, f of 0 minus h minus f of 0 minus h. So this will be limit h tends to 0. So 1 plus 2x is our function. So 1 plus 2 into 0 minus h minus f of 0 will be 1 divided by minus h. So this will be limit. One point I have missed here. If you will check at 0, they must give the same value. You should also check that, because minus half to 0 it is continuous and 0 to half it is continuous. So what will be the left hand limit and right hand limit? So if you will try to substitute or you can try to calculate, you will get that it is a continuous function. So I skipped that step. You can do that. So here it will be 1 minus 2h minus 1 divided by minus h, and if you will solve it you will get 2 here. While calculating the right hand derivative, f of 0 plus h minus f of 0 divided by h, this will be limit h tends to 0. So our function is 1 plus 1 minus 2x and 2px. So 1 minus 2h and 2ph plus 1, and when you will substitute 0 here you will get 1 and 1. So it will be 1 giving you the value 1 divided by h, and when you will solve it you will get, so this will be minus 2p minus 4p h square minus 2h plus 2ph divided by h. So from here you will get minus 2 plus 2p. Since we want our function to satisfy the Rolle's theorem, so must be these two derivative or left hand derivative must be equal, left hand and right hand. So this value must be equal to the f of 0 plus h minus f of 0 divided by h. They must be equal. So this will be 2 is equal to minus 2 plus 2p, and when you will solve it you will get p as 2. Just for a sake of clarity, we are checking whether f of minus half is equal to f of half or not. What is f of minus half? When you will put minus half here it will be 0, and when you will put half this will be 0. So this is also satisfying. So now all the conditions of Rolle's theorems by f is being satisfied with keeping in mind that our value of p is nothing but 2. So this is our answer. Clear? So now, since we have now recalled that you can say Rolle's theorem, now we let us move to mean value theorem. So in case of mean value theorem, we discuss two theorems, that is Lagrange mean value theorem and Cauchy mean value theorem. So let me write the first one, Lagrange mean value theorem statement. So Lagrange, I'm writing in short mean value theorem, MVT. So what is this statement says, or it states that let f of be any function from closed interval a b to r. Okay, and if f is, first one, continuous on a b, second one is differentiable on open interval a b, then there exists a c in ab such that, again here I will write with some different pen, f of b minus a is equal to f dash of c. So let me choose some. There exists at least a c. There exists at least one c in AB such that this condition hold, or this result hold. So let me draw it, how it will look like then. Suppose this is your graph. Okay, so I am saying that clearly this function f is continuous because it is not breaking anywhere, and it is differentiable as there is no peak. Okay, when you try to draw, what does this say? What is this quantity? Can anybody tell me what is this quantity? Can anybody tell me?
What is the question?
Positive.
Positive, it is correct. Does this quantity representing something?
Slope of a line joining the points a comma f of a and b comma f of b.
Correct. So if you will say that, and this must be equal to some f dash c. So if you will see that here, this is, so that means you are getting some c such that the derivative at that c giving you the same value of the slope of function on the interval ab. Okay, and if you notice that this Lagrange mean value theorem is nothing but it is the generalization of Rolle's theorem. Can anybody tell me how it is a generalization of Rolle's theorem?
It is just somehow rotated diagram.
Because if f a is equal to fb, then f dash is equal to 0.
Correct. See, what we are missing here, we are just missing the condition fa equal to fb that was in Rolle's theorem. So if you will consider here, although it has been discussed in the lectures by sir, I am just repeating it. If f of a is equal to f of b, then this will reduce to the Rolle's theorem. So then Lagrange theorem will behave as Rolle's theorem. This is I just told for the understanding, nothing more than that. Now let us discuss one question regarding this Lagrange mean value theorem, how we can apply that. So question number 3, let f and g are two functions on 0 to infinity to some real numbers, and these are defined by f of x is equal to x square minus x sin x, and g of x is equal to cos of x. Now applying Lagrange mean value theorem, we can conclude that I'm giving you the 4 options. The first one is f of x is equal to g of x for exactly two values of x. Second one is f of x is equal to g of x for more than two values of x. Or more than two values of x. Third option is f of x is equal to g of x for you can say exactly one values of x or exactly one value of x. And last one is fx is not equal to gx at any place for one exactly one value of x. And the D point is, D option is fx is not equal to gx on whole interval 0 to infinity, or for any value of x. You can say for any x in 0 to infinity. Now try this one, then we will discuss it. This is a simple application of this Lagrange mean value theorem.
Option C.
Correct. So let me explain why option C. So since we want to talk about fx equal to gx, so what we will do, we'll consider a new function. Let hx is equal to fx minus gx. So what it will give, what is fx? X square minus x sine x minus cos of x. So clearly you can say that h is differentiable. So what will be its derivative? X 2x minus x cos of x minus sine of x plus sine of x. So this will be x into 2 minus cos x. Over this domain 0 to infinity, can you say anything about this quantity? Can we comment anything?
Always positive. It is never zero.
Good. Since we know that our function cos x lies between minus 1 to 1, so this quantity will be positive, and since our domain is positive, so this will be positive. So on, or you can say for all x in 0 to infinity. So now you are able to know that your h dash x is greater than 0. Okay. Now how we will use this one? I am going to give you some new application of Lagrange mean value theorem that is quite commonly used. So what is h of 0? Can anybody tell me?
-1.
It will be minus 1. Some less than 0 quantity. What is h of pi?
Positive,
I
positive.
square -1.
Minus 1 or plus 1?
Plus one, plus one.
Plus 1. Plus
Plus
1.
1. Plus 1. So this is a positive quantity.
Yes,
So
yes.
if you will observe anything graphically like this, see what
Yes.
derivative told you. Derivative is greater than
If
0.
some
That means, yes, please.
if something is going from negative to positive, then it must cross zero.
Exactly.
So we can say exactly one
Yes.
root. It
But
must have one root.
see, we know that at h equal to 0 it is negative, and at h equal to pi it is positive. But there must be guarantee that it must be increasing function. Okay. So here, oh sorry,
Our
it will
our
be,
FTSX is guaranteed, na?
yes, yes, yes. I'm just
Always positive.
explaining. I'm just explaining further.
Yes. Okay, sir. Okay, sir.
So it is pi. At pi, it is giving some pi square plus 1 value. This is some pi square plus 1 value. And at 0, it is minus 1. So obviously, it must cross. I'm just drawing a graph. You can say. Obviously, it must cross your x-axis. So there must be a root. Okay. So that is what an famous application of this Lagrange mean value theorem. So since h of 0 into h of pi is less than 0, then h has a root, or you can say at least one root in which interval?
Open interval 0 pi.
Good. Open interval 0 to pi, because we know that at 0 it is negative, at pi it is positive, so there must be some point in between them. So that means there must exists some x naught, I'm writing just to be precise, x naught is 0. If h at x naught will be 0, so that means f of x naught will be g of x naught. Till now, can you mute yourself, Dr. Pushpinder?
Oh, yes.
Thank you. So till now we know that we got the existence of at least one point for which f is equal to g. Now we need to prove that this is a unique point. How we can do that? Did you able to understand my question, or shall I repeat it? Anyone?
There should be only one x naught. You wanted to mean it.
Yes. So how we will prove that? Any idea? Any guesses? See, so for this case, we let, if possible,
We can take assumption to,
exactly, if
and then
possible,
we can
yes,
contradict.
correct, correct. If possible, let there exist. See, one more is benefit we also are going to have, that h dash is 0. So it will definitely does not come to cross again this x-axis. You can also see that. If a graph is starting from negative and it is always increasing, so obviously it is obviously going to never going to cross again the x-axis. One reason is basic reason, geometrical interpretation is like this, and theoretically it is like that, this only. If possible, let there exist some number x1 in R such that f of x1 is 0. Now can we apply the Rolle's theorem on x naught to x1? F satisfy all the assumption of Rolle's theorem on the interval x naught to x1. Can I say this? Anyone? Anyone have any
Yes, sir.
objection? See, f of x naught is 0, f of x1 is 0. So obviously f of x naught is equal to f of x1. It is continuous, it is differentiable in between that interval. So ultimately all the conditions of Rolle's theorem will satisfy. So that means then there exists a C in x naught to x1 such that this h dash of C is 0. Can it be possible in our case? Can this scenario will be possible for any value of C? See, here you have proven that h dash x is 0 on whole domain, strictly greater than 0. Anyone? So this is a contradiction, or you can say which is not possible, which is not possible, as h dash x is strictly greater than 0 for all x 0 to infinity. Hence x naught is unique, or you can say that fx equal to gx for exactly one value of x. Is it clear? If you have any doubt, you can ask.
Rolle's theorem has been applied for the function hx.
Yes, for the hx. Okay, so I wrote here, sorry. I wrote here f. So, thank you. Is it correct now? Okay, so let me move to one.
But,
Yes,
but
can
the
you go ahead?
question was to apply with Lagrange, na? So
Yes,
how can exactly do with Lagrange?
see, this is the inbuilt application of Lagrange's theorem, or you can say inbuilt result of Lagrange's theorem. See, Lagrange's theorem guarantee you about the continuity and differentiability, and it is the mixed results of that Lagrange's theorem. You can say it is a corollary of that result. Okay.
Okay, sir.
Yeah. So next one is
Sir, h dash c is greater than 0 throughout the interval
yes,
because it is strictly increasing function in that interval.
yes. I mean greater
My-
than zero, then only we can say that it is a strictly increasing function.
At that interval means 0 to pi.
Sorry, can you repeat it?
Repeat, my hx is strictly increasing function in the interval 0 pi.
No, it is strictly increasing function on whole domain 0 to infinity.
0 to infinity.
Yes,
How?
you can see it here. This is h dash
Oh,
x.
h dash is greater than 0. It is already proved h dash is greater than 0
Yes, already we have proven
for
that.
all x.
Yes. So
That means h dash c also greater than 0.
it should be greater than 0, but it is coming out to be equal to 0. That means we have assumed something wrong. So that means there must be unique root. Okay. So this question will be a clear application of Lagrange mean value theorem. Earlier was indirect application or an indirect application. So suppose this is a function, be a function satisfies f dash of x is equal to 1 by 6 x square minus 9, and f of minus 1 we know that it is ln of 2. Now using Lagrange's mean value theorem, find the estimated interval I such that f of 0 can lie in that interval. So we need to estimate an interval I, a suitable interval such that our value f of 0 can lie into that interval. So try this one. This is the direct application of Lagrange mean value theorem. Earlier was something different. Does anyone have any idea how we can approach this one?
Can we apply Lagrange's mean value theorem
Yes.
-1 to 0.
in the interval -1, 1?
No, we see. We
We have to talk about 0, so we have to stop at 0 now.
Yes.
That's why we can
See,
create an equality like this.
yes, Manish. So we want the value, or we want the estimated interval for this f of 0, or you can say at x equal to 0. And we know that the value f at x equal to -1. So obviously, for very smartly, we need to apply Lagrange's mean value theorem over the interval -1 to 0. That will be the suitable approach. So using
In -1, 1 or -1, 0?
-1 to 0, because we want the value
0.
0. Using
Okay.
Lagrange's mean value theorem on the interval -1 to 0. So if we will apply the Lagrange mean value theorem over this, what we can have, f of 0 minus f of -1 divided by 0 minus -1 f dash of some c. Is it correct output of this theorem? So
Yes.
we don't know the value of f of 0, but we know the value of f of -1, that is ln2. And we also know that what is f dash x, that is 1 by 6x square minus 9. So it will be 1 by 6 c square minus 9. Now it is very easy to check that this function, which value can contain, or which value, what will be the maximum or minimum value in this interval. Can anybody guess it? See,
Maximum and minimum value of a right hand side.
yes, this c square minus 9, or you can say 1 by c, 6 times of c square minus 9. What will be the maximum or minimum value for this function?
Minimum -1 by 54.
Okay, for whole function, minimum -1 by 54. Are you sure?
Let me check, sir. Let me check.
Yes,
Let me
please,
check.
please. That is maximum value. Your answer is correct. You have one bound, but that is a maximum bound, not the minimum one. See, our c lies between -1 to 0. So our c square must be lying between 0 to 1. -9 c square minus 9 will lie -8. And where this reciprocate lies? Now what was our function? 6 times of this quantity. Anyone have any doubt over this? Although our c lies from here, where our c lies? Open interval -1 to 0. That is why I wrote strict inequalities in all these lines. Do anyone have any doubt in this bounds estimates? Shall I proceed?
Yes,
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 sir.
yes, sir.
Okay. So f of 0 minus ln2 will also be lying between -1 by 48 to -1 by 54. So that means f of 0 must be lying between these two values, or you can say this will be the interval. F of 0 must belongs to the interval I and the interval I is defined as ln2 minus 1 by 48, comma ln2 minus 1 by 54. Clear? Now, next question is based on Lagrange mean value theorem and Cauchy mean value theorem. So let me recall the statement of Cauchy mean value theorem. This Cauchy mean value theorem is also known as generalized mean value theorem. This is a generalization of even Lagrange mean value theorem. You will get to know soon how. We will discuss that also. So let f and g are be two functions. So I'm writing directly, let f and g are defined from a b to r. Okay, and if f and g, these both are continuous on ab, differentiable on open interval ab, and we need one more condition, that is g dash x does not vanish anywhere in the interval ab. Then we can guarantee, then there exists at least one c in ab such that g of b, oh sorry, f of b minus f of a divided by g of b minus g of a is equal to f dash of c divided by g dash of c. So earlier I told you this is a special case, this is a generalized case of even Lagrange mean value. Can anybody tell me how it is a generalization of Lagrange mean value? What was the
If we consider gx is equal to x,
if gx is equal to x, then this Cauchy mean value theorem will,
is converted to Lagrange mean value theorem.
okay, it's converted into, that is a better one, is, or you can say reduced
Okay.
to Lagrange Lagrange's MVT. Okay, so what problem I want to discuss is like this. Consider the functions fx is equal to sin x and gx is equal to x square, where x belongs to 1 to 2, then which of the following equations can be obtained from Lagrange's and Cauchy's MVT for some C1 comma C2 from 1 to. So these are some, can say, equations. 2C1 cos C2 is equal to 3 cos C1. Second one is 3C1 cos C2 is equal to 2 cos C1. Third one is 2C1 cos C2 is equal to 3 cos C2. And the last one is 2C2 cos C2 is equal to 3 cos C1. So you need to apply Lagrange theorem or Cauchy mean value theorem and tell me which of the following equations you are going to get. You need to use both the theorems. Try this one.
Hmm? Begin.
Could you please mute yourself? So let us apply Cauchy mean value theorem on f and g. So on this interval 1 to 2, clearly g dash x is not equal to 0 for all x in 1. So definitely it's going to be in the denominator. So apply Cauchy's mean value theorem on the interval 1 to 2 for f and g. So this will give us f of 2 minus f of 1 divided by g of 2 minus g of 1 is equal to f dash of c1 divided by g dash of c1, where c1 belongs to open interval 1 to 2. Is it clear? Now it is simple to calculate the value of g of 2 and g of 1. So if you will see that this will be 4 minus 1 something, or very smartly what we can do, f of 2 minus f of 1 divided by 2 square minus 1 square. This is f dash of c1 divided by, what is f dash of c1? Cos of c1. What is g dash of c1? 2 times of c1. So if you will try to write this as 2 minus 1 and divide by anything 2 plus 1, can we write like this? Anybody having any doubt? Okay. Now, is it something recognizable?
Yes, some Lagrange's mean value theorem, left hand side part of.
So apply Lagrange's mean value theorem to, or you can say for f on the interval 1 to 2. So what you will get? F of 2 minus f of 1 divided by 2 minus 1 is equal to f dash of some c2. So obviously earlier we have used c1, so here must be something different c2, 1 to 2. So from here you will get the value of f of 2 minus f of 1 divided by 2 minus 1 is equal to some cos of c2. So by 1 and 2, what you can you mute yourself please? By 1 and 2, thank you, you will get cos of c2 divided by 3 is equal to cos of c1 divided by 2c1. So from here it will be 2c1 cos of c2 is equal to 3 times of cos of c1, and this is given in which option? This is given in option number A, 2 times of c1 cos of c2. So this is option A. Okay, so in the question number 6 we are going to use Taylor series or you can say Taylor formula, Taylor polynomial, Maclaurin series. There are some very different names of this series. Obviously you can, they are something different, is something mint different. So let me recall what is Taylor series first of all. So Taylor's theorem I would write, then there will be cases where we call it formula, where we call it polynomial, or So we write this one for any f at center at x naught. So f x can be written as, just a second please, yeah, f of x naught plus f dash of x naught x minus x naught divided by 1 factorial plus f double dash of x naught divided by 2 factorial x minus x naught whole square plus, let me write plus here, and the nth term will be f nth derivative at x naught divided by n factorial x minus x naught power n plus some remainder term. This is Taylor's formula or Taylor's theorem, I would say. Now from here, when we call it Taylor's polynomial, when we call it Maclaurin series, or when we call it Taylor series, can anybody tell me? See, till the part of this one, we call it without remainder term, we call this one Taylor's
Polynomial.
polynomial, correct? When we call it Taylor series,
If Rnx remainder term tending to 0,
correct. If Rnx goes to 0 as n tends to infinity, so that means this, you can say this looking like a polynomial structure, it will go to infinity. And the final one is when we call it Maclaurin.
if we put x is equal to 0, sorry, if x naught is equal to 0,
Yes. So in the same scenario, if x naught is 0, Maclaurin polynomial will be the nth polynomial of this Maclaurin series. Okay. So let me give you one question, direct question of this Taylor's theorem. Find the Taylor's.
Sir, Maclaurin polynomial is the nth polynomial. I can't understand what are you want to say.
Okay, okay. You understood this Taylor's polynomial?
Yes, sir. Yes, sir.
So this is Taylor's polynomial of f at x naught, center at x naught. Okay. So I am saying Maclaurin series is nothing but you just need to put x equal to 0. So whenever you put x equal to 0 in this Taylor's polynomial, you will get Maclaurin's polynomial. Correct? So,
Okay, sir.
yes. So find the Taylor's polynomial of degree 5 of the function fx is equal to sin x around the point x equal to 0. So this is a direct. So here you can even say that you were asking Manas. So here you can also say it as find the Maclaurin's polynomial of degree 5 for this function. So that means it is understood you need to find out the polynomial for x not equal to 0. So this is a direct formula based of this. Kindly find out quickly. We need to only calculate till degree 5, or you can say here you need to just process till fifth order derivative, you can say. So we need to calculate the derivative till fifth derivative value at x equal to 0. So we know that f of x is sin x. So what will be the value of f of 0? F dash x is, so what will be the value of f dash of 0?
1.
F double dash x will be, so f double dash 0 will be,
0.
f triple dash x will be, so f triple dash 0 will be
Minus 1.
f fourth derivative
0.
fifth derivative is,
Plus 1.
so now let us write what will be its Maclaurin series, or you can Maclaurin polynomial, or you can say what will be its Taylor's polynomial at x equal to 0. So p5 of x, you know that you can write f of 0 plus f dash of 0 divided by 1 factorial x minus 0, and till f5 of 0 divided by 5 factorial into x to the power 5. So this will give us, first one is 0, so that means it will start from x minus x cube by 3 factorial plus x to the power 5 by 5 factorial. Is it clear? Or any doubt?
Clear, sir.
Okay. Now let us move to the next question, number 7, which is a bit indirect problem based on this Taylor's Maclaurin series, I can say. So find the value of the real number alpha so that the coefficient coefficient of x to the power 50 in the Maclaurin series expansion of alpha x square e to the power x is 1 by 48 factorial. See, we need to tell what will be the coefficient of x to the power 50. So first of all, you need to find out what can be the, or you can say what can be the general term for this Maclaurin series. So you need to calculate f at 0, f dash at 0, f double dash at 0. So there will be some inductively, or you can say some you will get some equation that is depending on n. So you can some sequence, so you can directly guess what will be the value of this alpha. So let me start this one. What is f of x here? Alpha x square e to the power x. So what will be the value of f of 0? Obviously 0.
0.
F dash x will be alpha x square e to the power x plus 2 times of alpha x e to the power x. Again f dash of 0 will be
0.
f double dash x alpha x square e to the power x plus 4 times of alpha x e to the power x plus um, 2 times of alpha e to the power x. Now what will be the f double dash 0? 2 times of alpha, correct?
2 alpha. Yes, yes.
What will be the triple derivative? Alpha x square e to the power x plus you can say 6 times of alpha x e to the power x plus 4 times of from here you will get 4 and from here you will get 2, so this will be 6 times of alpha e to the power x. Then again f triple dash 0 will be 6 alpha, correct? So here if you will observe that, or you can do only one more derivative, then you will able to see what will be the sequence depending on n it is coming out to be. So this will be 8 alpha x e to the power x plus from here it will be 12 alpha e to the power x. So f fourth derivative at 0 is 12 of alpha. So from first if you will observe that this is nothing but 2 into 1 into alpha, 3 into 2 into alpha, 4 into 3 into alpha. Is it visible? So what I can say that fn of 0 is nothing but n
N into n minus 1 into alpha.
correct. So if you know that what is fn at 0, then obviously you know that what is the coefficient of x to the power 50 in the Maclaurin series. Coefficient of x to the power 50 in Maclaurin series nothing but 50th derivative at 0 divided by 50 factorial. Am I correct?
Yes.
So we know that value of f50 at 0, 50 minus or 50 into 50 minus 1 into alpha divided by 50 factorial.
তুমি ফ্যানটা অফ করলে চলে যাবে বেশি তোমার তোমার কারেন্ট নিয়ে কথা
Sir, can you
কারেন্ট
mute
বন্ধ করে
yourself?
তার মানেই তো তাই হচ্ছে
Can you mute yourself, please?
তুমি বন্ধ করে চলে যাও বেশি ভয় করো না
So this is given as 1 by 48 factorial. So from here if you will observe that alpha is nothing but 1, because 50 will cancel out, 49 will cancel out, you will left with the 48 factorial. Is it clear to everybody?
Yes, it is clear.
Okay, thank you. Yes, Manas, please ask.
No, sir, clear.
Okay. So next we are going to do some application of these Taylor's theorem, that is some kind of indeterminate form that we will use to calculate some indeterminate limits. So these things can be directly explained by questions or problems. So I am directly writing the problem and then we will discuss its solution. So before that, just let me quickly say that what are the indeterminate forms. So let me just only write how we can recognize that this is an indeterminate form or this is or which one is not. So 0 by 0, is this an indeterminate form or not?
Yes, it's an indeterminate form.
Infinity by infinity,
This is also
0 into infinity,
this is also
infinity minus infinity.
Yes.
yes.
So these are indeterminate forms. There are some more that are 0 to the power 0, infinity to the power 0 and 1 to the power infinity. Dr. Pushpinder, thank you, please. So, what are not indeterminate forms? That are 0 to the power infinity is an indeterminate form. Anyone?
0 to the power infinity is not indeterminate form. This is 0.
And infinity into infinity, or you can say infinity plus infinity. Infinity.
Both are infinity.
Correct.
All are infinity.
So this
And
is
last one is 0.
0. This is infinity. This is infinity. This is infinity, and this is 0. So these are some, you can say, confusing indeterminate, seems to be indeterminate form, but these are not indeterminate forms. So I just let you know. Now let us move to the question. Which of the following is or are correct? The first one is limit x tends to 0 positive x square divided by under root of x plus 1 minus 1 is 0. Second one is limit x tends to pi sin x divided by x square minus pi square is equal to 2 pi. Limit x tends to 0 secant x minus 1 divided by sin x is equal to 0. And the last one is limit x tends to 0 minus x square is 0. So we need to calculate these limits by the help of recognizing its indeterminate form and applying the L'Hopital rule. So let me tell you what is L'Hopital rule. L. So it is pronounced like L'Hopital, not L hospital. So it is applicable only on these two indeterminate forms. Whenever you feel like your function is coming out to be, or your form is coming out to be like this, you can say that this limit is nothing but f dash. You can do the derivative separately. So in the solution, if you will see the first form, limit x tending to 0 positive x square divided by under root of x plus 1 minus 1. So which form it is like? 0 by 0, or it is not any kind of indeterminate form?
0 by 0.
0 by 0. So since it's a 0 by 0, we can apply L'Hopital rule. So do the differentiation
Yes,
of the
sir.
numerator separately. It will come out to be 2x. And what will be the differentiation of denominator? It will be 1 by 2 under root x plus 1. So this will give us limit x tends to 0 plus 4 times of x under root of x plus 1. So this will be 0.
0.
So it is correct. This one is correct. Second one is limit x tending to pi sin x divided by x square minus pi square.
It is incorrect.
Okay. What is, first of all, tell me it is a indeterminate form or not, and which indeterminate form if it is?
This is indeterminate from 0 by 0.
0 by 0. So it will be cos x divided by 2x. So now it will be minus 1 by 2 pi. Correct? Or did I wrote something wrong?
No, it is all right.
Okay. So this is given as 2 pi. So that means this option is not correct.
Incorrect.
Limit x tending to 0 secant x minus 1 divided by sin x. Again it is a 0 by 0 form, so you can calculate as
Yes.
secant x tangent x divided by cos x. So it will be 0.
Yes.
So this is correct. Now the last one is minus x square ln x. So limit x tending to 0 minus x square ln x. Which kind of form it seems to look like? 0 by 0, infinity by infinity, anything?
Infinity by infinity. After
Yes, exactly.
shifting x square term in the denominator.
Exactly. Currently it is like 0 into infinity kind of form. When you will send x square into the denominator ln x, and I'm writing like minus 1 by x square. Now it will be infinity by infinity. So limit x tending to 0, this will be 1 by x and this will be 2 by x cube. So this will be limit x tending to 0, x square by 2, which will be 0. So this is also correct. Is it fine?
Yes.
Now let me give you one more problem based on this indeterminate form. Find the value of a and b from R for which the following limit exists. And what is the limit? Limit x tending to 0, 1 by ln into 1 plus ax minus 1 by tan inverse bx. So we need to find out the value of a and suitable value of a and b such that our limit exists. Try this one. You just need to identify the indeterminate form, then you need to apply L'Hopital rule appropriately and tell me the values of a and b quickly. Can anybody guess in which form currently it is? Which indeterminate form it is?
0 by 0 after
No,
Currently,
it is infinity minus infinity.
currently it is infinity minus infinity,
cur-
but
currently it is, yes, but after rationalizing.
yes, rationalizing.
My bad. After taking LCM.
Yes, tan inverse.
After simply subtracting.
So this will come out to be limit x tending to 0 tan inverse bx minus ln 1 plus ax divided by tan inverse bx into ln 1 plus ax. So now it will be in
0 by 0 form.
0 by 0 form. Now you can apply L'Hopital rule. So when you apply L'Hopital rule, the first term will be b by 1 plus b square x square. Correct? second term will be a by 1 plus ax. What will be denominator? B times ln 1 plus ax divided by 1 plus b square x square, and with positive sign this will be a tan inverse bx divided by 1 plus b square x square. Now tell me, when you now you if you will substitute 0 x equal to 0, will it be still in any indeterminate form?
No,
So
it,
it will
it
not,
has a definite value.
it will have a definite value.
Value.
So when you will when you are substituting x equal to 0, what you will get, what you are getting in the numerator, you are
B
getting b minus
minus A.
a divided by,
B plus A.
but it will be 0 na, ln 1.
Yes, ln1 is 0.
So it will be,
That means 1. 1 plus A.
why 1 plus a?
1 plus 0. Simply 1.
I don't think so.
In denominator we have 0 na. In denominator we have 0. So denominator is tending to 0. So B should equal to A.
Good,
So B
correct,
should equal to A first. B
correct.
should equal to A.
So understood. See, if you will put directly, so it will be b into 0 and this will be a into 0 something. So this will come out to be something by 0. So limit will not exist again. So what there should be a case, if b equal to a, then what will happen? If b equal to a, then what will happen?
0 by 0 form.
0 by 0 form again come out. Then you
If
can
B
differentiate
is
it
equal to
again.
0, lekin if B is equal to 0, numerator is exactly 0, not tending to 0.
So I am saying b equal to a.
Yes, yes, sir. B equal to A.
So if I am assuming b equal to a, in that scenario our above equation will reduce to minus a by 1 plus ax divided by a ln 1 plus ax divided by 1 plus a square x square plus a tan inverse ax divided by 1 plus a square x square. Now if you will solve it x tending to 0, you will get a common outside, 1 plus ax minus, or you can say write it ax minus a square x square, and 1 plus a square x square. Okay, here I made I think mistake. Here it will be 1 plus ax, so it will be 1 plus ax. So again here it is also 1 plus ax, so it will be 1 plus a square x square and 1 plus a times x divide. So this will cancel out, this will cancelling out. You will left with a common, 1 plus ax ln 1 plus ax plus 1 plus a square x square tan inverse of ax. Tell me if I wrote anything wrong. I'm sure it is correct. So again it is a 0 by 0 form. Do anybody have any problem to see that it is again 0 by 0 form?
Yes, sir. It is correct.
Yes, it is 0 by 0.
Okay, so now you will differentiate again. So you will get a minus 2a square x divide by first of all this will be a plus a times of ln 1 plus ax plus b, oh sorry, b a plus 2 times of a square x tan inverse of ax. Any doubt? Now if you will substitute x is equal to 0, will it be still in indeterminate form? Obviously not. Your answer should be 1 by 2. So the limit exists for a equal
Wait,
to
wait, it last. 5 minutes, 10 minutes.
Vishwajit sir, please mute yourself. So your answer will come out, or your limit will exist when value of a is equal to value of b. So you have many choices, but just one condition, a should be equal to b.
So in order to existing the limit, we have to assume a is equal to b.
Yes, exactly, you are right. So one question I am just giving you for your homework. If you will not able to get, you can discuss with me in the next tutorial. Evaluate the value of limit x tending to pi by 2 plus function is sin x to the power x minus pi by 2, and I am just, for a sake of ease, I am telling you its answer is 1. And you can observe that which kind of form is this? 1 to the
1 to
power,
the power infinity.
0 to the power 0.
no,
1 to the power infinity.
1 to the power,
1 to the, yes, 1 to the infinity.
yes. Now you can try this at your own. If you have any doubt, we may discuss in the next tutorial session on next Tuesday. So
Sir, next class will be next Tuesday at 6 p.m.
yeah, same time, next Tuesday 6 to 8.
Okay, thank you.
Yeah,
We will get a mail, na? We will get a mail.
yeah, you will also get a mail reminder. You will
Okay,
get.
okay.
So any other doubt?
No, sir.
Okay, thank you.
Yes.
Thank you.